Hi and welcome to my video on integrating polynomial rational functions part 2. I'm going to look at a very special case that's kind of the only chain rule type case that we can do. So as we move through integration, you're going to see more and more that we can do simple expressions, so polynomials, exponentials, etc. But we can't do the complex ones. It's really hard to do the chain rule, product, quotient rule type questions in reverse. We cover a lot of that in the specialist math course, but not so much in math methods. So I'm going to show you a couple of cases now, or one in particular, and then later on you'll see some others where we can do that. So let's start with defining the function we're going to deal with. I'm going to show you how to integrate the function ax plus b to the power of n. And with respect to x, and of course, this could have a constant at the front. It could be like c times ax plus b to the power of n. That would be fine. The c would just stay there and remain a constant multiplier, so I'll leave it out for now. This is the worst possible chain rule you could get for integration at this stage. And it's just a linear function on the inside. So there's my linear function raised to the power of some number. So a, b and n are just numbers. The best way to explore these sometimes is to think, well, if I derived a function in this form, what would the derivative look like? And it's really important to track the a, b and n and what happens to those. So let's do that, shall we? Let's imagine that I've got y is equal to ax plus b to the power of n. It could be negative a, it could be negative b, so a and b can be negative numbers. And I want to know dy dx. I do dy dx is equal to, I would bring the power down, n, times ax plus b to the power of n minus 1, and then I would have to multiply by the derivative of the inside function. This is like my speedy way of doing the chain rule. Of course, you might be able to do it even quicker. Basically, the derivative of this is a, and so I get a times n times ax plus b to the power of n minus 1. So what that means for me is that if I integrate an to the ax plus b to the power of n minus 1, I know it's looking a bit out of hand here, I get this. It integrates to give ax plus b to the power of n plus some constant. So this is an an factor at the front, whatever that is. It's just an additional factor. This is kind of the rule. There's not really a rule that exists for this one, but let me write down a rule that probably is better, because we wouldn't normally start with n minus 1. So if you were integrating instead ax plus b to the power of n dx, which is what we started with over here, well, that wouldn't be too hard. We would just write it down as ax plus b to the power of n plus 1, raise the power by 1. But recognise down here that we didn't end up with just a factor of the new power, we ended up with a factor of the a. So I'd have to divide by a, and I'd have to divide by n minus 1. And of course there's a plus c. So I get this function here, it's a linear raised to a power, and that linear raised to the power goes to n plus 1, we increase the power by 1, and then we divide by, that should be n plus 1, sorry. We divide by a, which is the coefficient of x, the derivative of the inside function, times by n plus 1. Now, it'd be worth exploring what happens if this is not linear. What if this is quadratic? The problem then is the derivative of the inside function is not just a number. It's an expression now, it's got x, isn't it? So it's got a variable, which means we're dividing by a variable, and if we came to redifferentiate that, we'd actually have a quotient rule that ends up a lot more complex. So it doesn't quite work, but this works. Let's look at one simple example. The integral, I'll say simple, maybe I won't make it too simple. The integral of 7x plus 2, that part's pretty simple, but it's always going to be pretty simple. But let's say we make it to the power of a half dx. The rule still holds, there's no change. So to integrate this, I get my 7x plus 2. I raise the power to 3 over 2, so a half goes to 1 and a half, which is 3 over 2. But now I have to divide by 3 over 2, so that 3 over 2 is my new power. But I also have to divide by the derivative of the inside function, which is 7. And that 7 is the coefficient of x. So they're my things that I have to divide by. And of course I have plus c. Now it's a little bit mucking around with fractions here. 7x plus 2 to the power of 3 over 2 divided by 21 over 2. Dividing by 21 over 2 is the same as multiplying by 2 over 21. So it becomes 2 over 21, 7x plus 2 to the power of 3 over 2 plus c. And you can put that back into square root form if you needed to, or whatever it is you need to do to simplify it. But that's how we follow that through, and that's actually a pretty hard one. This rule applies up. And this rule, verbally, don't forget, if you've got a linear function raised to a power, that when you integrate, in fact, any polynomial, consider it. When you integrate a polynomial, you raise the power by 1, divide by the new power, but also divide by the derivative of the inside function, just in case, and the linear term will give us that. And there we go. Happy days.